Our next talk is by Wibisono. Andre is an assistant professor at Yale University. He was a PhD student here in Berkeley and did postdocs in Madison and Georgia Tech. He has done a lot of very, very interesting work on optimization and sampling and the combination of the two. And I believe this talk will be in that spirit. And he gives great talks and also does very interesting work. So I'm excited for this one. Well, I'm excited for all the talks, but this one is closest to what I do. Okay, please go ahead.
Thank you. Thank you, Elena. Hi, everyone. Thank you for attending this talk. My name is Andre Wibisono. I'm at Yale University. And this is joint work with my colleagues, Ruiden Lee, Mole Tao, who's in the audience, and Santosh Kampala at Georgia Tech, where I did my postdoc previously. So the talk will be about this algorithm called the mirror Langevin algorithm. So let me start by describing what the problem we are trying to solve is, and then let me try to give a motivation from a continuous time perspective why we are studying this kind of dynamics, and then I'll tell you about the main result and the proof technique using what's called the mean square analysis. Okay. So this is a sampling problem where the goal is we want to draw a sample from a probability distribution, let's say nu, and we assume that nu has a density of the form e to the minus f on some domain X constrained in the Euclidean space, right? So here we assume that the density with respect to the Lebesgue measure, and we are in the first order setting. So we assume that the function f, which is the log density, is differentiable, and we get access to the gradient information. Thus, the goal is to design an algorithm to draw samples using this information. And of course, this has a very, very nice theory and connection to optimization, right? For example, the problem of log concave sampling when the domain X and the function f is convex has a lot to do with convex optimization. And furthermore, as is the theme of this workshop, of this whole program, we can view sampling as an optimization problem in the space of probability distribution. So most of the talk will be concerned with the constraint setting when the domain X is a proper subset of the Euclidean space. But since this is the beginning of the workshop, let me try to remind us all about what happens in the unconstrained setting. So the unconstrained setting, when we want to draw a sample from the whole, from a distribution nu supported on the whole Euclidean space, there are various techniques we can do. Like for example, in continuous time, we can use what's called the Langevin dynamics, which is the following stochastic process, which looks like gradient flow for minimizing f plus Brownian motion, right? And it is a remarkable fact that this actually draws sample from the target distribution e to the minus f asymptotically as t equals to infinity. And in discrete time, we can try to discretize these dynamics, and that gives us what's called the unadjusted Langevin algorithm, where here it looks like we are doing a gradient descent step plus a Gaussian noise of some step size, right? And there are a lot of very nice convergence analysis of these algorithms when this function f, the log density, is convex, right? And when we say convergence analysis, we have to specify what kind of distance we are using. And as a reminder, there are some really nice distances, right? For example, here's what's called the Wasserstein distance, which is the induced by optimal transport. Or we can use some notion of divergences, like KL divergence, which is relative entropy, or chi-square divergence. And these two are, of course, not symmetric, so they're not real distances, but nevertheless, we can use them to measure convergence to the target distribution nu, right? So, for example, in continuous time, this Langevin dynamics, so this has an optimization interpretation as the gradient flow for minimizing KL divergence or relative entropy. If we work in the space of excuse me, in the space of probability distributions P over the Euclidean space using the metric given by the W2 distance. And so this was the seminal work by Jordan, Kinderlehrer, and Otto from 1998. And this interpretation gives us a lot of very nice guarantees for this continuous time dynamics. For example, when the target is strongly log concave, then we know that this actually has exponential contraction in Wasserstein distance. And not just that, we can actually relax this condition and say that as long as the target distribution satisfies some inequalities, some isoperimetric inequalities, such as the log Sobolev inequality or Poincare inequality, then we can actually show an exponential convergence guarantee in either KL divergence or chi-square divergence, right? So this says that in continuous time, we have a really good mixing time bound with logarithmic dependence on the error on 1 over epsilon. However, in discrete time, this question is a lot more complicated, right? In discrete time, if we look at the following unadjusted Langevin algorithm, we know that this is a biased discretization in the sense that in the limit, it converges to a distribution mu sub h, which is different from your actual target, right? And the bias, the distance between this bias limit and the true target scales with your step size, right? So when you translate that, this gives you a mixing time bound with a polynomial dependence on 1/epsilon instead of logarithmic. So, and we can make this formal, and we can show there are now really good mixing time bounds for W2 distance under strong convexity, for example, by the work of Taloyan and Drumu and Moulin and a lot of other people. And we can also do it under a slightly weaker condition, for example, log Sobolev inequality. And one way to address this issue is we can also correct the bias with an accept reject step, and the resulting algorithm called the Metropolis Adjusted Langevin algorithm, or MALA, recovers the log 1/epsilon dependence, but only in total variation distance. Right? And I think we'll see a few talks about this this afternoon. Okay, so this is what happens in the unconstrained setting, right? So now let's go to the constraint setting where suppose the domain X is actually a proper subset of the Euclidean space, right? Either like a polytope or a sphere, and we want to draw a sample from a distribution supported on this space, right? For example, the problem of uniform sampling from a polytope is a very important problem, and that's still very difficult. So there are a lot of approaches to do this. One basic approach is to say that, well, let's just run the usual Langevin algorithm, and whenever we go outside, let's just project back to the space. So that's what's called projected Langevin algorithm. And you can analyze this, and there is a mixing time bound, for example, by in the work by Bubeck et al. But in some sense, this is not very satisfactory because we really do not want to go outside at all. What happens if we want to stay inside at all time? So another idea is to use a metric, let's impose a metric on the space such that we cannot go outside at all. Right? So one idea is one algorithm is called the Deakin walk, and this is a modification of the ball walk where we draw samples from what's called the Deakin ellipsoid defined by the Hessian of the log barrier function. So this is a similar idea to interior point methods in optimization. And this has nice analysis using self-concordance barrier property. And so for example, by Ravi and Hari Narayanan, it shows that when we want to draw a uniform sample from a polytope in D dimension with M facets, it has complexity proportional to M times D. And recently, it's been improved using notion of weighted barrier function and what's called strong self-concordance. It actually has faster mixing time bound, another D squared. So this is a very, very nice theory. And a related approach to this is what's called the mirror Langevin algorithm, which is what we study in this algorithm. So here we also use a barrier function, but we use the gradient of what's called the mirror map to map it to the dual space. And then we do the updates in the dual space. We do a Langevin algorithm or some other updates, and then we map it back to the previous space. So this is similar to what's called mirror descent in optimization, right? So this algorithm was proposed in this paper by Zhang et al. At CODE last year. And there was also an earlier related approach using a slightly different dynamics by Xie et al. That appeared a few years earlier. Okay, so what is this algorithm? The algorithm looks like the following. So here we want to draw a sample from distribution of the form e to the minus f, and the update looks like we choose phi, which is called a Legendre function, and we use the gradient to map the domain X to the dual space, and then we do the Langevin update in the dual space, except that the Hessian of your phi also appears as the covariance in the Gaussian noise, right? And in some sense, this is the sampling analog of mirror descent, because you can also write this in a form that's more reminiscent to mirror descent, where you're saying that your next point is obtained by minimizing some linear function, right? This is just a constant vector, plus the Bregman divergence generated by your function phi. So without this additional randomness, this becomes the mirror descent algorithm. It turns out that if you add this Gaussian noise with this covariance, then this gives you a sampling algorithm. And you can ask, why do you need to add this? Where does this come from? And it turns out that where it comes from, one way to say it is that this comes from discretizing what's called the mirror Langevin dynamics in continuous time, which is the following stochastic differential equation in terms of y, which is the gradient of phi of x. So this looks somewhat nicer because now we don't have the step size, but then you can still ask, why is this the right dynamics to use for sampling? Right? Where does this come from? So let me try to give a very high-level overview of what happens in continuous time. And a lot of this was also covered in the bootcamp tutorial a few weeks ago. So let me try to just go quickly. So what happens here is that we are in the metric setting where we work with a convex subset of Euclidean space, but we treat it as a manifold. Okay? So at every point x, we endow it with a metric G, written as a positive definite matrix G of x, and we use that to define the notion of local inner product at each tangent space, right? So at a point x, you have this tangent space, and you measure the inner product between two vectors u and v by multiplying it by this G matrix, right? And the Euclidean setting, Euclidean matrix, the case when G is the identity matrix, but you can put a lot of other G, right? For example, a nice case is the Hessian metric when G is the Hessian of a convex function phi. So if we have this setting, what do we do for optimization, for example? If we want to minimize a function f, then we can run the following Riemannian gradient flow, where the curve x follows this differential equation, where here this gradient of f is the L2 vector of gradient of partial derivatives, and then we multiply it by the inverse metric G to turn it into a proper Riemannian tangent vector, right? So formally, the vector partial derivative is a differential in the cotangent space, and then you need to map it back to the tangent space by this inverse metric. But as an ODE in RD, this is what the Riemannian gradient flow looks like, right? And then this gives you a lot of nice information. For example, you can say that if f is strongly convex in the geodesic sense, meaning it's strongly convex along geodesics defined by your metric G, then this is an exponentially contracting curve. And turns out you can also relax that. For example, if the function f satisfies what's called the gradient domination condition, or this is what's called the PL inequality usually, but now with respect to the metric G, right? So this definition, this norm sub x here is using this definition where you have this metric G here. But if you have this inequality, then you can show that the function value decreases exponentially fast along your gradient flow. So this is for any G. And then it turns out that a nice case is when we have a Hessian metric. And then this is what's called a natural gradient flow, usually in the literature. And you can try to discretize this. When you discretize this, you get what's called a natural gradient descent, where it looks like you're doing gradient descent, except that you also multiply by this inverse Hessian, the inverse metric. So this was studied by Amari, for example. But one of the issues is that this algorithm requires Hessian information, right? So instead, what we can do is let's look at this dynamics in the dual space, right? So in the dual space, meaning that we apply this gradient of phi, which we call the mirror map, to map the domain x to the dual space y. So anything we can do in the primal space, we can do in the dual space, right? If I have a function f here, I can push it forward to get a function f tilde here by saying that my f tilde is just f composed with the inverse map, right? So that if I map x to y, then my function value f of x gets mapped to the function value f tilde of y, right? And similarly, what's really nice in this setup is that the metric, the Hessian metric defined by phi on this space, gets pushed forward to Hessian metric here, which is induced by the dual function phi star. Right? And that happens, that works because we are mapping by this mirror map. So there is a very nice duality condition here. And then it turns out that in the dual space, natural gradient flow becomes what's called mirror flow. Right? And this mirror flow is also the natural gradient flow for minimizing this push forward function under this push forward metric. And then discretizing this gives us the mirror descent algorithm for optimization. And the advantage is that now there is no Hessian involved. This only involves the gradient. Right? So this is what happens for optimization. Now let's see what happens for sampling. We want to look at what are all these things when we want to do sampling sort of optimization. So let's go back to our constraint sampling problem where we want to sample from some domain, and we impose some metric G on the space, right? So what kind of dynamics should we use? So the analog of Riemannian gradient flow is the following thing called Riemannian-Langevin dynamics. So this looks like Langevin dynamics with some drift and some Brownian motion, where as before, we multiply the gradient by the inverse metric, but then that inverse metric also comes up in the covariance of the Brownian motion, as well as in this correction term in the drift, the divergence of the inverse metric. So this has been studied a lot previously, classically, right? For example, in this reference. And you can see that in the Euclidean case, you don't have this term here, and this divergence becomes 0. So this gives us back to usual Langevin dynamics. But in general, you have this covariance and this correction term. And these are there so that overall, this dynamics has the correct stationary distribution, which is proportional to e to the minus f, where f is whatever appears here, right? And you can ask, like, how do you check something like that? One way to say it is to say that if x follows dynamics from this SDE, then the density rho evolves following a PDE, which is called a Fokker-Planck equation. And the form looks like the following, where the inverse metric, your covariance here, just appears here, just multiplying the gradient of the log density. And then from this, you can see that when rho is equal to nu, the right-hand side becomes 0. So nu is a stationary solution. Right? And moreover, the optimization interpretation still works. That this is also the gradient flow for minimizing KL divergence, but now using the Wasserstein metric generated by this metric G on the base space, right? And then all the conclusion before about exponential convergence rate and isoperimetry, we can also say when everything's defined with respect to this metric G, right? Okay, so this is the general structure. And now let's ask what happens in the Hessian case. So suppose we use a Hessian metric when G is the Hessian of some convex function phi. And then this gives us what's called the mirror Langevin dynamics, where everything here was G before, and we just replace it by this inverse Hessian. Right, so this is nice, but it still looks somewhat complicated because of this term mostly, right? This is a divergence of the inverse Hessian, so it looks complicated. But then recalling what we did for optimization, when we map to the dual space, mirror flow becomes really nice. Here we can do the same trick, that in the dual space, let's map it from X to Y via this mirror map. And it turns out that this mirror Langevin dynamics becomes something that's much simpler, right? Because the drift term simplifies just one term. There is no inverse Hessian involved, there is no divergence involved, basically because everything cancels out when you do the calculation. And here the Hessian of phi is replaced by the Hessian of phi star. And this is because the metric, this Hessian metric is pushed forward to this Hessian metric of phi star by the mirror map, right? And then discretizing these dynamics gives us the mirror Langevin algorithm, right? So, so this was the dynamics that was studied by Zhang et al. And also a follow-up work by Chui and Philip and co-authors, where they study that this dynamics has very nice properties in continuous time. Right? So for example, if the target distribution, so the target in the primal space is e to the minus f, and then the target in the dual space is just the push forward of that e to the minus f by the mirror map. And then we can say that if the target satisfies either log Sobolev or Poincaré with respect to the Hessian metric, so what's called the mirror Poincaré inequality in the paper, then we can conclude an exponential convergence in KL divergence or chi-square divergence, right? Okay, so let's see. Okay, so this is not the topic of this talk. Maybe I won't spend too much time here, but a very, very nice property happens when you choose phi to be equal to f, right? Because then you can see that the gradient of f cancels out with the gradient of f star. And that's what gives us what's called the Newton-Langevin dynamics. That was studied by this paper by Sinho and Philip and co-authors. And a remarkable property of these dynamics is that the Poincare inequality of your distribution, either minus f, with respect to its own Hessian metric, is always true. And that's because you can show that it's equivalent to what's called the Brascom-Lip inequality, which is a classical inequality that holds for any log concave function f. Sorry, for any strictly convex f. Right? So this says that along this dynamics, along this Newton-Langevin dynamics, the chi-square divergence converges exponentially fast for any log concave nu with a uniform rate. Right? And interestingly, this dynamics in fact also appeared in an earlier work by Fatih from a different perspective, from a Stein-Kernel perspective. Okay, and maybe let me skip this one, but in the optimization setting, this is what the corresponding property that happens. Okay, so now let's go back to discrete time. So hopefully that gives us a brief overview of why we care about the dynamics that we study. But now let's look at what we can say in the actual discrete time algorithm. So again, this is the mirror-Langevin algorithm. This was first proposed and studied by Zhang et al. As a discretization of the mirror-Langevin dynamics, which we just saw. And what they showed in the paper is that they showed that the iterates of this algorithm have a convergence, has a bias convergence, where the bias is non-vanishing, meaning that the bias does not go to zero if you scale the step size to zero. So a bit more concretely, so they assume a set of conditions. One of them is the following property called modified self-concordance. So this is an assumption on the choice of the Legendre function phi. So the assumption is that the square root of, as a matrix, the square root matrix of this Hessian is Lipschitz in the Hilbert-Schmidt norm with some parameter alpha. And essentially, what they show is that the bias of the algorithm scales as something that goes to zero with step size, plus an asymptotic term that depends on d, the dimension, and alpha, this parameter here. But there is no step size here, right? So as you scale the step size to zero, you still get this term. So what this means is that what they show is that the iterates of the algorithm converge to a ball around the minimizer, but we're not sure yet if it actually converges to the solution, to the minus f. Yes, there's a question. What is the one? Are these sharp bounds? In some sense, no. So part of the question here is that, so they conjecture that this bias, this non-vanishing bias is unavoidable, essentially because we are discretizing something with a multiplicative noise. And so what we show is that, in fact, with a slightly more refined analysis, we can remove this, this bias. And then we get a term that looks like that. But yeah, but so this observation and this conjecture motivated the question of, do we need either a better algorithm? Maybe we need a more sophisticated discretization of this of the dynamics, or can we just analyze this in a better way, right? So on the front of a better algorithm, there were a few follow-up works, including an alternative discretization by Kwang-Jun An and Sinho Chui, where we apply this two-step process where we take a gradient step in the dual space that looks like mirror descent, and then we solve the Brownian motion part exactly. A Brownian motion part with this, with a star here. This Brownian motion part with this changing covariance, right? And what they show is that if you analyze this algorithm, you can show a vanishing bias with a very, very nice analysis using nice conditions such as self-concordance and using convex optimization tools more closely. However, this requires solving these dynamics, which may be difficult for general phi, right? So, okay, with that setup, what we show is the following. We studied the basic algorithm of mirror-Langevin algorithm, the same algorithm they proposed previously. And we show that, in fact, it has a bias convergence with a vanishing bias, meaning that the bias goes to zero with step size. And moreover, we only use a subset of the assumptions in the original paper. And what I will show in the rest of this talk is that a proof technique using what's called the mean square analysis framework And in fact, we will apply that to the dual space. Remember that this is the primal form of the mirror Langevin algorithm. If we look at the dual variable y mapped by the mirror map, then it looks a little bit simpler. So in the y space, it looks like we are doing, we are taking a step along this direction with a Gaussian noise with this covariance, right? Okay, so more precisely, so here are the assumptions that we need. So we assume the following. We assume that the choice of the Legendre function phi satisfies modified self-concordance, which means the square root of the Hessian is Lipschitz in the Hilbert-Schmidt norm with parameter square root alpha. And we also assume that the function f is smooth with respect to phi, which means that the difference of the gradient of f is brought above by the difference of the gradient of phi. And moreover, it is strongly convex with respect to phi, which is the following. And you can look at the name and see that when phi, in the Euclidean case, when phi is a quadratic function, this becomes the usual smoothness condition. This becomes the usual strong convexity condition, right? And when phi is quadratic, this becomes, this is trivial because this the left-hand side is 0, so alpha is 0, right? But for general phi, this alpha can be non-zero. So in the paper by Zhang et al., they also assume some other conditions which we don't need. So these are the 3 conditions we use. And our result, okay, so before that, so we can also translate these conditions in the dual space, right? So in the dual space, in terms of y, which is the mirror map of x, let's define this matrix A of y, which is the square root inverse Hessian of phi star, and this vector G of y, which is the gradient of f composed with gradient of phi star. Then you can see that this property translates to the property that the matrix A is Lipschitz in the usual sense, right? And this f being M smooth with respect to phi says that this vector G is also Lipschitz. And strong convexity with respect to phi says that this vector G is monotone in the usual sense. So in the dual space, all these conditions become the usual nice conditions that we have previously. And here's the main result. So assume, so this should be A1, A2, A3. And the main important requirement is that the self-concordance parameter alpha is bounded above by M/2, where M is, so alpha is the parameter here in the self-concordance, modified self-concordance, and little m is the strong convexity constant. So we require that this alpha does not go too large. It has to be less than M/2 here. Then there is a choice of maximum step size such that the algorithm, mirror Langevin algorithm, has the following bias convergence guarantee in the dual space, in the y variable, that after k iterations, your W2 distance between your iterate and the target, right? So nu is a target in the primal space, and then we push it forward by the mirror map to get this target in the dual space. So your W2 distance is bounded by the following. There is one term that goes to 0 with k, with the iteration. And then there is another term that scales with the square root step size. So this is the bias term. And moreover, this constant c is also explicit. It's on the order of square root dimension. Yes, question?
Quick question. This assumption that alpha is less than M/2. Could you just always make that hold by scaling up f?
Right, so the question is, this condition alpha less than M/2, does it? Can you always make it work by scaling up f? I think so. Yes, right. So if you choose phi, it has some alpha, and then if your m does not work here, you can scale f so that satisfies a condition. Yes, right. So this condition says that we may not be able to sample from E2 minus f, but we can sample from E2 minus f over some constant. Yeah. So this is in the dual space, and you can see that in the primal space, it has the same guarantee because everything just gets mapped by this mirror map, right? But notice that here, this is convergence guarantee in the W2 distance in the Euclidean metric, right? Not not using the Hessian metric. And this W2 distance here is with respect to this induced mirror map. So this is the same distance that they used in the original paper by Zhang et al., right? But in particular, this shows that the bias actually scales with square root d times h. So there is none of this asymptotic non-vanishing bias. And then as a corollary, as usual, right? So what if you want to make this less than epsilon? You can set both of these to be less than epsilon, then that gives you a mixing time bound. Right? So this says that if we want to get W2 distance less than epsilon, then we can run this algorithm, but the step size h scales with epsilon squared, right? And then we need to run it for some iterations that scales with essentially 1 over the contraction factor times step size, right? So step size scales as 1 over epsilon squared. So then this gives us this mixing time bound on this order dimension over epsilon squared, assuming that all the other parameters m and big M and so on are dimension free for now. So if you compare this with ULA in the unconstrained Euclidean setting, right? So you can show, for example, a typical result is to say that under smoothness and strong convexity, the bias scales as dimension times h, right? So then the missing time bound is d over epsilon, right? And a more recent result by Lee et al. Shows that if you also have a third order smoothness condition, then you can improve this dimension to be square root dimension. And then that gives us missing time bound of square root d over epsilon. But instead, for this mirror Langevin algorithm, the bias scales as square root step size, right? And that's what gives us this 1 over epsilon squared dependence. And this is essentially because we are discretizing an STE with what's called multiplicative noise, with changing covariance. So we lose an order. Okay, so that was the result, and then for the rest of the talk, I'll try to describe the proof technique using mean squared analysis framework.
Wait, before you go there, can I ask a quick question?
Yes.
How do you, when you specialize this to phi equals f, what does so I know that A2 and A3 are basically free with m equals 1, but what does A1 give you? What does it say on f?
Yeah, no, very good question. So the question is, what happens when phi is equal to f when we are in the Newton case? So these are always true with m equal to 1. Here, it just says that your f satisfies this condition, that the Hessian of the square root inverse Hessian of dual function is Lipschitz. So I'll have an example later. So in one dimension, this is equivalent to saying that phi is self-concordant in the classical sense, but in higher dimension, this is not the same. So this condition, so part of the discussion in the end will be that this condition is in some sense not ideal because this is not a finite invariant, for example, whereas the classical self-concordance condition is very nice. It's a finite invariant and so on. So we would like to replace this condition by something that's more natural. But yeah, but for general F, this is not a free condition. You have to check this. Okay. Sorry, how much time do I have?
4 or 5 minutes.
Okay, maybe let me not go into the detail of the mean squared analysis, but my colleague Morita is here and happy to chat more. But the very high level idea is that mean squared analysis is a very general, powerful framework for bounding the error between a discretization algorithm and a continuous time process, right? So maybe let me show you the before that. So classically, in the classical setting, we can so this is a very classical technique from analysis and physics and so on. But classically, we can only show bounds up until some constant iteration. But it turns out that if we assume that in continuous time the process is contracting, then we can control the error so that we can conclude the bound for all time. So we get a global bound on the error between the algorithm and the process. So this was analyzed and proposed by this paper by Lee et al., the Xuechen Lee, Danny Wu, Nasser Maki, and Murad Erdogdu at NeurIPS a few years ago. But for this talk and our work, we will use a more recent extension by Lee et al., Ruilin Lee, Hong Yuan Jia, and Morita, which has a slightly weaker requirements on the error that allows us to apply this for the algorithm. So let me skip the setup, but the assumption is the following, that in continuous time, we assume the process is contracting. That if you take any two synchronous solutions and you let them run, they have to converge exponentially fast. And furthermore, the diffusion has the following what's called deviation bound, that in short time, they cannot actually deviate too much. And then we also have condition on the algorithm, that if I give you a discrete time algorithm, there is a notion of what's called local weak error and local strong error. And this bounds the difference between if you start at the same point and you let a diffusion process run and you let an algorithm run, you want to bound the error between these 2 points, right? The local weak error is error in the expectation, and the local strong error is error in the R2 norm. Right? So previously, in the previous work, these constants D1 and D2 are 0, but now in this more recent work that we use, we can have the following weaker condition. So here are the assumptions for the mean square analysis, that the important part is that the continuous time process is contracting and your discrete time algorithm has bounded error orders. Now the conclusion is that there is a maximum step size such that for all time, you can bound the error between your discrete time algorithm and your continuous time solution. And the bound does not depend on K. The bound scales out your step size to what's called the strong error order -1/2. Sorry, I'm skipping a lot of detail here because just to give you the idea, and we can compute the constants explicitly. So yeah, and for the proof, you can show it satisfies the following construction, the recursion. But let me show you how we apply this to our algorithm, right? So for our algorithm, remember this is the in continuous time, the algorithm comes from the mirror Langevin dynamics, and we have the following 3 assumptions. And what we show essentially is that these 3 assumptions imply that all the assumptions in the mean square analysis framework are satisfied, and then we can conclude the mixing time bound. Right. So, please check out the paper for the detail, but we show that the assumption alpha less than m/2 implies that the dynamics is contracting with this rate m-2 alpha, right? And we can check the division bound also. Let me skip the proof. And moreover, we can check that the discrete time algorithm has the following error orders. So P1 is 3/2 and P2 is 1, right? And we can also track the constants explicitly. So then the proof of the main result is to say that, well, all those conditions actually imply that we satisfy the mean square analysis assumptions. And then we can conclude the following guarantee, which is our main result, right? So yeah, so please check out the paper if you're interested, or happy to talk to. And let me finish by just mentioning some discussion about this result. So this is what we show, that we show this W2 mixing time bound has this bias, which implies the following mixing time bound. But here are some questions. So one is that everything right now is in the Euclidean metric. We would like to have something in the Hessian metric, right? Or in other distances, in other measures. The conditions right now assume this relative smoothness and strong convexity. So they do not work, for example, for sampling from uniform or Gaussian if we use log barrier function. Essentially because for this barrier function, you want the Hessian to go to infinity on the boundary. So you want so this implies your F also has to go to infinity on the boundary, right? So can we weaken this assumption? And then a related question is this notion of modified self-concordance. In one dimension, it's the same as the classical notion of self-concordance, but in higher dimension, it's not the same. So here's an example that you can show that for the polytope or the log barrier function. So remember that this satisfies self-concordance with parameter 2, right? Classically. And then it turns out if you do the calculation, the modified self-concordance parameter of this function can be as bad as 1 over the squared smallest singular value of A, your constraint matrix. Right? And you can make this as bad as you want. So even in 2 dimensions, so here's an example. You look at this polyhedron, so this intersection of 2 half spaces. You can choose explicit points, and you can compute this ratio, and you can achieve this bound 1 over epsilon squared. So you can make this to infinity. right? So we would like to have something with a more natural self-concurrence condition. And finally, the current technique uses continuous time contraction as part of the assumption. So can we weaken that? Can we have an analysis where the continuous time process is just converging, not contracting? And so we know how to do this, for example, for ULA, but can we do it with this multiplicative noise? Okay, so thank you so much. That was our result, and please check out this preprint and let us know if you have any more questions. Thank you.
Sure. Just a question about the mirror maps. Is it easy to actually find those?
Is it easy to find those? Part of the assumption is that you have to be able to compute this. You want to justify so that you can compute this gradient easily and this inverse map easily. So for some nice functions like entropy and so on, you can do that. But in general, the choice is that you also have to satisfy all these conditions, right? So for now, the result is still somewhat restricted. Right.
Okay, thank
you. Yeah. So when you try to use the basic MLA, I'm still a little confused why it's biased when you let h go to 0. So basically, you are saying when you let h go to 0, it will not converge to a continuous limit?
It will. It will. The dynamics itself will, right? So the in continuous time, it comes from this Miron-Jevon dynamics. But part of the issue was that so the previous work shows that in terms of the W2 bound, there is a bias that scales with step size plus this something that does not go to 0. And the question was that was this an artifact of the analysis or was this inherent to the algorithm? Essentially because we are discretizing something without changing covariance. Right? Okay. For ULA, when this was a constant, we did not have this term. Also in the Euclidean case, when phi is quadratic, right? So alpha is 0. So then this term disappears. So this recovers the correct result for ULA, but not for MLA. And part of and part of our contribution is to say that this really was an artifact, and we can do a more refined analysis.
There's one more question, and then we'll all go out for a break.
Yeah, so I have one question. So so does a condition alpha less than m/2, is it because it's needed because is it because of numerical side or the analytic side about whether it's about the convergence of the continuous time dynamics or about the numerical error?
Yeah, thank you. So the question is this constraint on m and alpha. So right now it's needed in the calculation because I skipped this slide earlier, but if you have two synchronous solution and you compute the difference between their L2 norm, the difference of the square covariance happens here. So here you can see why modified self-concurrence is a natural condition to use. And the term that comes out, the constant is m-2 alpha. So that's the condition. But you can also see that in general, we need some bound alpha on the Lipschitz constant of this one to make sure the STE converges. And so you can look at, for example, the geometric Brownian motion, which is the following STE. You can check that there is a threshold that if alpha is above 1, this diverges. When alpha is below 1, it converges to 0. So there is a different behavior depending on the Lipschitzness of this covariance. But it's not clear if we can relax this. Really, we would like to.
Thank you so much.
Sure.
Okay, so let's continue the discussion with some caffeine and sugar outside. And let's first thank Andre again for the great talk.
Thank you.
And we'll be back at 11:30.
Still gonna be 0.